Hi guys, today we're going to be starting section 6.4, which is going to be creating the graphs of the sine and cosine functions. Before we get into their graphs, I just want to remind you guys about how these trig functions work. We've talked about it quite a few times. Remember, trig functions are functions of an angle. That means they depend on an angle measure. So angles go into the trig function and a ratio of two side lengths comes out, right? So that means that the angles go in as x, they will go into the function, and then the y value, f of x, the ratio is what comes out. So the ratios come out as the y coordinate. So all of the ordered pairs that live on the sine and cosine or any trig functions graph, the x and y coordinates represent an angle as x and a ratio as y. So we want to talk in terms of x and y now when we move to the actual coordinate plane. So that means that x will be an angle and the y value will be a ratio on all of these trig functions graphs, okay? Now, since angles go in as x, we have to measure the angles in radians and not degrees anymore. We want to be in radians at all times because a radian is a real number. When you measure an angle in radians, you're trying to figure out the number of radii that fit into the length of that arc that created that size angle, right? So they're always measuring an angle as a real number. Where when you think about it, degrees are not measuring the angle as a real number. They're measuring it as a degree. So when you think about it, when we measured angles in degrees, that made us rotate around the coordinate plane in a circular motion, right? When we were measuring angles in degrees, it took us in a circle, right? Here was 0 degrees. Here was, as that angle kind of fans out, here was, let's say, 45 degrees. And then we fan out some more. Here was 90 degrees. We fan out some more. Here was 135 degrees. We fan out some more. Here was 180 degrees. We keep fanning. And now here was, let's say, 225 degrees, etc. So when you measure an angle in degrees, it sends you in this circular motion. So if we want to travel horizontally across the x-axis, we need a real number measurement as x, and that's what a radian does. It measures the angle as a real number, okay? So in order to move along the x-axis in a horizontal direction, the angle must be measured in radians, a real number measurement. So guys, now we're gonna have to be in radians as we use the x-axis to represent our angles, our inputs, and our ratios represent our y values. So when you start graphing these trig functions, they're actually going to form what we call waves, all right? So when you measure an angle, and let's say we do the sine function, y equals sine x, right? So when you plug a radian measurement in, the sine of pi over 6 is 1/2. So an angle went in and a ratio of 1/2 came out. All right, pi over 2 radians. What is the sine of pi over 2? Well, what's the sine at 90 degrees? What was that? It was 1. So now we have pi over 2 went in as the angle and a ratio of 1 came out. And you have these ordered pairs that you can now start forming. But guys, remember, at the end of the day, these are real number measurement. Pi over 6, 30 degrees, a radian measurement of pi over 6, literally that number is pi divided by 6. Pi divided by 6, that's a number of 0.52. That is 0.52. That's a real number. Pi over 2, that's literally pi divided by 2, that's 1.57. That's a real number, 1.57 radians, but it's a real number. That's literally where 1.57 would be on the x-axis as a real number. Pi radians is literally 3.14 radians. That's where the number 3.14 would really be on an x-axis. So just keep that in mind. If we're going to travel horizontally across the x-axis and not in this circular motion, you have to be in radians because radians measure angles as real numbers. 0.52, 1.57, 3.14, etc. They're measuring the angles as a real number. And that's going to allow us to travel horizontally along the x-axis by using these real number angle measurements. Okay, so when we graph the sine function, let's just remember a few things first, okay? The 6 trigonometric functions are periodic functions. That means they're going to repeat. After so many units, they start to repeat themselves and they form cycles. So after so many inputs go in, they're going to make the exact same graph over and over and over again. Now we saw in the other section that sine, cosine, cosecant, and secant all have a period of 2 pi radians. Every 2 pi radians, every complete rotation around the unit circle, they start to repeat the outputs. But the tangent and the cotangent function, they repeated faster. They had a period of pi radians. Every pi radians, their graph starts to repeat and form the exact same picture, all right? All right, there's another word we have to add to this when we start looking at their graphs in this horizontal direction. It's called the amplitude. The amplitude of a function is half the distance between the maximum and minimum values. It's half the distance between the highest and lowest point of the function. We'll point that out when we actually see the graph. I'll show you what the amplitude is, okay? So let's do this. Let's graph y equals sine x on the coordinate plane, okay? Okay, so the easiest angles to actually use when you're just trying to whip up a quick sketch are your quadrantals. Your 0, your pi over 2, your pi, your 3 pi over 2, your 2 pi, and so on. They're the easiest ones because they have the nicest sine and cosine ratio, zeros, ones, negative ones, and so on. So those are the angles that I'm going to use to whip up the sketch of the sine function. I'm going to use my quadrantals, my zeros, my pi over 2, and so on. So basically what I'm doing is I'm counting by pi over 2. We're starting at 0 radians, and we're going to go to 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, 4 pi over 2, which is 2 pi, 5 pi over 2, 6 pi over 2, which is 3 pi, 7 pi over 2, 8 pi over 2, which is 4 pi. It's 2 complete rotations around the circle and so on. So we're literally just going to count by pi's over 2 because those are the nicest angles to use. So I've made you a chart where we're going to start at 0 radians, and then every pi over 2 radians we're going to plug an angle in. So 1 pi over 2, 2 pi over 2, which, guys, that's pi. All right, 3 pi over 2, 4 pi over 2, which is 2 pi, 5 pi over 2, 6 pi over 2, which is 3 pi, 7 pi over 2, 8 pi over 2, which is 4 pi, 9 pi over 2, 10 pi over 2, which is 5 pi, 11 pi over 2, 12 pi over 2 is 6 pi, so that would be your third complete rotation around, and so on. So we're just using our quadrantal angles, and we're just rotating around and around and around over and over and over again. I even went in the negative direction, so that's negative 1 pi over 2, negative 2 pi over 2, which is negative pi, negative 3 pi over 2, negative 4 pi over 2, which is negative 2 pi. So it's one complete rotation in the negative direction, and so on. All right, so let me label my x-axis. 0, 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, 4 pi over 2, which is 2 pi, 5 pi over 2, 6 pi over 2, which is 3 pi, 7 pi over 2, 8 pi over 2, which is 4 pi. So this would be your second complete rotation around. All right, and then I'm going to go in the negative direction. Negative 1 pi over 2, negative 2 pi over 2 is negative pi, negative 3 pi over 2, and then negative 4 pi over 2 is negative 2 pi. So that's one complete rotation in the negative direction. All right, so again, these are just the easiest angles to do because they have the nicest sine ratios. All right, so here we go. So watch what happens. I'm just going to use my unit circle. First, we're going to plug 0 in. 0 radians, the sine of 0 radians. Well, at 0 radians, the y-coordinate is 0. So that's 0. So when an angle of 0 radians goes in, a ratio of 0 comes out. So that's 0, 0. That's the first point on the sine function's graph. All right, now we're going to plug in pi over 2. The sine of pi over 2 radians. Well, at pi over 2, the ratio is, represented by the y-coordinate, is 1. So when an angle of pi over 2 radians goes in, a ratio of 1 comes out. Okay, now we're going to plug in pi. Pi radians, the sine of pi radians. Well, at pi radians, the y-coordinate is 0. So when pi radians goes in, a ratio of 0 comes out. Okay, now we're going to plug in 3 pi over 2. What is the sine of 3 pi over 2 radians? Well, at 3 pi over 2, the y-coordinate is -1. So the ratio is -1. So 3 pi over 2 radians went in, and a ratio of -1 came out. Okay, now we're going to plug in 2 pi radians. What is the sine of 2 pi radians? Well, at 2 pi, now we've gone all the way around, right back to where we started. At 2 pi radians, a 0 comes out. So now at 2 pi radians, a 0 comes out. So really quick, we said that the period of the sine function is 2 pi radians. So we just went 2 pi radians. So that means that right here, when you fill these dots in, that is one complete rotation around the unit circle in forms of angles. So that is what one rotation of the sine function's graph looks like. This is what we call a cycle. From 0 to 2 pi is his period. So this is one complete cycle of the sine function. Now, when you go to plug 5 pi over 2 radians in, well, guess what? 0, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. My fifth 90-degree angle, he lands in the same spot as pi over 2. So all the same outputs are going to start to come out again. So 0 came out again, now 1's going to come out, and then 0 is going to come out, and then -1's going to come out, and then 0 is going to come out again, because you'll have made another complete rotation around. All right, so this is what we call, this is what one cycle of the sine function looks like. That's your sine wave. This is what one rotation around looks like. This is one complete cycle. This is what one period of the sine wave, what it's going to look like, okay? And like I said, you plug 5 pi over 2 in, your fifth 90-degree angle lands right here. So again, it's a ratio of 1. So 5 pi over 2 comes out, goes in, and a 1 comes out. Now you plug in your sixth, right? 1, 2, 3, 4, 5. My sixth 90-degree angle lands in the same spot as pi. That's a ratio of 0. So that 3 pi radians goes in, and a 0 comes out. 7 pi over 2, my seventh 90-degree angle. 1, 2, 3, 4, 5, 6, 7. My seventh 90-degree angle lands in the same spot as 3 pi over 2, and a ratio of -1 comes out. So 7 pi over 2 goes in, and a -1 comes out. 4 pi, which is the same thing as 8 pi over 2, 8 90-degree angles. My eighth 90-degree angle, 1, 2, 3, 4, 5, 6, 7, 8. My eighth pi over 2, my eighth 90-degree angle lands in the same spot as 2 pi. So a ratio of 0 comes out. And you've just done another complete cycle, another complete rotation around, another period has passed, and now you've created yet again another sine wave. And it's just going to continue like that. This is a periodic function, so the graph is going to look very repetitive. It forms the same picture after so many inputs. So again, we can just predict that the next wave would come like that. All right, we can even go in the negative direction and form him backwards. So at negative pi over 2, well, negative pi over 2 radians is right here in the same spot as 3 pi over 2. And the sine ratio is -1. So when negative pi over 2 goes in, a -1 comes out. Negative 2 pi over 2, your negative second 90-degree angle, -1, -2 is in the same spot as pi or negative pi, and the sine ratio is 0. All right, so negative pi goes in, and a 0 comes out. Negative 3 pi over 2 radians, well, negative 3 pi over 2, -1, -2, negative 3 pi over 2 is in the same spot as pi over 2, and the sine ratio is 1. So negative 3 pi over 2 goes in, and a +1 comes out. All right, and then negative 4 pi over 2, your negative fourth 90-degree angle, -1, -2, -3, -4. That's one complete rotation around in the negative direction. Your sine ratio is 0. So now when negative 2 pi goes in, a 0 comes out. And again, look, you've traveled -2 pi units this way. So again, from here to here, one cycle has been formed. You have yet another sine wave that has been formed. every 2 pi units, a sine wave is formed. That's the period. And then again, we can predict that his graph would just keep on going and creating more sine waves, okay? So that is the graph of y equals sine x. This is known as your sine wave. Okay, and the sine wave starts at 0. 0, 0 is where the sine wave starts, because cosine will be different, and that's how you'll know the difference between your sine wave and your cosine wave. Sine 0, 0. 0 radians go in, a ratio of 0 comes out. That's how we know it's the sine wave, okay? All right, so let's fill in some information that we know about it, all right? What is the domain? Well, who were your x values? Those were your angles. What angles were you allowed to plug in? Any angle you wanted. So the domain is all real numbers. Well, the range, what kind of ratios came out? Well, look at all the y values that live on this graph. They go from 1 to -1. So all your ratios for the sine function are in between -1 and 1. Okay, well, your x-intercepts, guys, you have infinitely many x-intercepts. Look, it touches the x-axis right here at 0 radians. It touches the x-axis again at pi radians. It touches the x-axis again at 2 pi radians. It touches the x-axis again at 3 pi radians. It touches the x-axis again at 4 pi radians. So you are going to have infinitely many x-intercepts. They're continuous. They go on forever and ever. So that means that, look at it, 0, 1 pi, 2 pi, 3 pi, 4 pi. The next one would be 5 pi and then 6 pi. They are integer multiples of pi. Okay, so the way we write that is we start at 0 and then we can go forward or backwards, plus or minus pi radians away. Every pi radians, there's another x-intercept, times k revolutions. Those form your x-intercepts. And then what's the x-intercept's y-coordinate always? 0. So all of your x-intercepts will be 0 plus or minus pi times k revolutions away from him, okay? All right, what did we say the period was? The period of the sine function, well, one cycle is from 0 to 2 pi. That is what your sine wave looks like. So your period is 2 pi. Every 2 pi radians, you form another sine wave, okay? So the period is 2 pi. The amplitude, well, this is new. It's half the distance between the highest and lowest point. Well, the highest point is 1, right? The highest it ever reaches is 1, and the lowest it ever reaches is -1. So what distance is in between 1 and -1? That's a distance of 2 units. Half that is 1. So the amplitude is 1 unit. So basically what I think of it as, think of the x-axis, the line y equals 0. It's kind of like the midline of the graph. And then the amplitude goes the same number of units up from that midline and the same number of units down. So if the x-axis is your midline, it goes 1 unit up from that midline and it goes 1 unit down. Your amplitude is the number of units up and down from that midline. So it's 1 up and 1 down, right? It's half the distance between the highest and lowest point. All right, so the amplitude of your sine wave is always 1 unit unless it's been transformed. All right, and then the y-intercept is right there at 0, 0. Okay, this is all information about the original sine graph before you've transformed it, okay? Well, if you remember, we said that the sine function is an odd function with symmetry to the origin, right? Look, the point pi over 2, 1 is on his graph, and the point negative pi over 2, -1 is on his graph. For every xy, there's an opposite of x and an opposite of y that lives on his graph. That's odd function behavior, all right? So it is an odd function with symmetry to the origin. Because by definition, odd functions have symmetry to the origin, all right? Now, if we just concentrate on, let me see if I can do this, one cycle. All right, if we concentrate on one cycle from 0 to 2 pi. All right, so if we just function on that wave right there, let me see if I can move that a little bit. All right, so from 0 to 2 pi, one cycle, one period. It is broken up into 4 subintervals. 1, 2, 3, 4. You have the subinterval from 0 to pi over 2. You have the subinterval from, well, and let me just say this. This subinterval from 0 to pi over 2, that's like those are your quadrant 1 angles. All right? The next subinterval is from pi over 2 to pi. Okay? And those are your quadrant 2 angles, the angles in between pi over 2 and pi. Then you have another subinterval between pi and 3 pi over 2. All right, those would be your quadrant 3 angles in between pi and 3 pi over 2. And then your fourth subinterval is from 3 pi over 2 to 2 pi. And those are your quadrant 4 angles, okay? So each period is broken up into 4 subintervals, 1, 2, 3, 4, right? If I go to the next period, the next cycle, again, it's got 1, 2, 3, 4 subintervals of x values, all right? Did you see that? I'm sorry, I don't know if it was on the camera. All right, the next period, the next sine wave also has 1, 2, 3, 4 subintervals, okay? And along those subintervals, the graph is made up of 5 key points, all right? 1, 2, 3, 4, 5 key points live on his graph for each cycle or each period. All right, your 5 key points. Well, the first one is 0, 0, and it's an x-intercept. The next key point is a maximum. It's pi over 2, 1. These are points. All right, your next key point is pi 0, which is an x-intercept. Your next key point is right here. It's a minimum value on the graph. It's 3 pi over 2, negative 1. All right, and then your last key point right here is 2 pi, comma 0, and it's an x-intercept again. All right, so these are the 5 original points that you should use when you go to transform them. So if you want to shift it up or down or right or left or vertically stretch it or horizontally stretch it, remember these 5 original ordered pairs. They are the 5 key points that live on the very first cycle of this graph's function, okay? Or this graph's wave, I should say. So just remember these 5 ordered pairs, okay? All right. I thought I had something else I wanted to say, but I think I'm going to wait till the next video. All right, so just to remind you, sinusoidal functions are transformations of the sine function. The cosine function we're going to graph next, his graph is actually just a transformation of this graph. He's a transformation of the sine function's graph. All right, I'll be back in the next video.